Hello, everyone, and welcome to this Texas Instruments Australia tutorial for QCE students. This afternoon, we are looking at exam preparation for the Specialist Mathematics course using TI-Nspire technology. Our presenters today are Stephen Broderick and Peter Flynn. Now I'll hand over to our first presenter, Stephen.
Welcome to the tutorial for Specialist Maths. I was going to look at a few little tips that could be useful using multi-choice questions and saving time during the exam. So these questions are from the QCAA Specialist 2020 mock exam for public use. So the first question is a velocity question and we have to find the acceleration. Now, I'll show you two different ways. First of all, we can use a calculator screen and this template here, the tools template, and we'll put in the derivative with respect to time, and our function is sine to the negative 1t, and we need to tell it the particular time. So this command here, control and equals, sorry, we need to put in, hit that again, control and equals, and we need this vertical line here to put in t equals 0.2. So this will find the derivative when the time is 0.2. So enter that, and you can see the answer is 1.02 meters per second squared. Now this is in a calculator page. This is actually locked, so you can't edit this. So a great thing you can do is use a notes page. So if we go into a calculator home and then click on a notes page, and we'll do the same thing again. So we'll pick the derivative template, and you'll notice with the notes page we've got this dotted line around the box. So the notes page is active when you're in there. If you step outside, you're not in the notes page, so you need to be inside that dotted box. So we'll put in sine to the negative 1 of t, and once again we need to put in this vertical bar and t equals 0.2, and you'll see the answer there, 1.02, which was answer B. Now the good thing about this notes page is you can edit that, you can change that to other values. So during a multi-choice question, you can quickly cycle through different values. So I highly recommend using a notes page. The next question is a complex number question. So there's 4 multi-choice answers. And I'm going to go straight into a notes page. So if we click on the home screen and then this yellow box, and we need the math box. So I don't think I mentioned that before, but if we hit the control and M for the math box, so just remember that, control and M, we can then put in a complex number, and sticking with the convention, if we use Z, and we want to assign our complex number. So if we hit control and then the template there, that will allow us to assign our complex number. So it was cos of, here's a fraction template here, cos of 2 pi on 5, and just make sure you jump outside there because we want to add in I sine. So I sine, and use the fraction template again, 2 pi on 5. So that's in cis form or trigonometric form. So if we hit enter there, it'll turn that into standard form. And then we've got our math box here, so we can easily raise that to the power of 4, because the question was looking at that, what's the imaginary bit. And you can see the imaginary bit is negative 9.51, which is answer A. Also, if you wanted to, you could use the command IMAG, and notice how it goes from italic, and it recognises that command, and you could put in Z to the fourth there, and it'll just give you the imaginary bit, so negative 0.951. Okay, moving right along. So next question is also on complex numbers. So we'll look at two different ways of doing this. So one way is by defining the function. So once again, using a notes page and a math box, Control M, and the function, so I'm going to call it P of Z, and we want to assign that, so Control and just here, so that's assigning, and it's Z squared plus 2I Z minus 5. Okay, so that's assigned. So once again, don't jump outside the math box. If you jump outside the math box, it won't say done. So now we've got our 4 alternative answers. We can now put those answers in, and with the math box, you can quickly edit them. So the first alternative is 1 minus 2i, and we hit enter, and we're looking for 0, because if that is true, then that will, if that's a factor, that will equal 0, but it doesn't. So what you can do now, you can go back, if you look at the previous answer, it was 1 plus 2i for answer B, so we can just edit that and change that to a plus. And B is no good, and if we look at the previous answer, the answer after that, C is 2 minus I, so we can easily edit the math box and put a minus in there, and remember we're looking for a 0, so the answer is C. Now the other way you can do this too is using the C polyroots tool. So when you're in a math box, if you go to the menu there, you can see all the calculations are here, and if we go to algebra, if you've forgotten the tool, it's the C polyroots tool. So if you just remember that C polyroots tool, you don't need the capitals, but this also works quite well too. So if I copy that, and I just need to tell it that we're finding the zeros with respect to Z, and just hit enter, and you'll see the 2 zeros there, and the one we were after was 2 minus I. So the C polyroots tool, very, very handy in the complex numbers, and the one that I think I use the most. So moving right along on to matrices, and this is a dominance question that was multi-choice as well. So we've got Team A defeated Team B, so they get 2 points. They had a draw with C, so they get 1 point, and they lost to D, so they didn't get any points. So that's the win-loss matrix and the points allocation. And if we look at the model that they want us to use, so n plus n squared plus n cubed to rank the teams. So once again, if we go to a math box, and I'm just going to, remember, Control M to get the math box in the notes page, and I'm going to assign n as the matrix, and we need to click on the matrix tool there, and it was a 4 by 4. Okay, so we just need to put our elements in. So it was 0, 2, 1, 0, and then 1, and then 1, 2, 0, 1, 2, 1, 0. So just checking that that's correct. 1, 2, 0. Okay. And just hit enter. And it's recognised that. So now we can look at m, the model, which was m plus m squared plus m cubed. So there's our model, and hit enter, and oops, try again, hit enter, and there's our elements. Now you can assign another matrix to quickly add those elements, so I might just do that. So I'm going to assign another matrix E that will sum up the rows for us, so we can go control equals, and E is just going to be a column matrix, and it's going to have 4 rows, and it's just going to be filled with ones. Oops, so just remember to hit enter and stay inside the math box. So then we can go to our model. Oops. Undo, sorry. Hit the wrong button. Okay. So grab our model, and copy, and then so we need that in brackets and multiply by matrix E. So what that will do, it will sum up all the rows. So you can see D's got the highest points, then followed by C, followed by A, and then B. So I think that was answer D. Okay. Now the good thing about the math box too, if we made an error, so suppose we made an error like I did before. So suppose this is actually a 0, so they had a loss there. Then if you edit that, then everything else will change. So you don't have to go back and do it all again. So the math box, because it's all linked, it's very handy if you've made a mistake when you're checking over your solution. You can quickly go back, and if you find the error, you don't have to redo it all again. Just a click of one change and you're there. Okay, the next one is the Leslie matrix. So we have this Leslie matrix model with 4 age groups. So we've got the birth rate up the top, and then we've got the survival rates going across here diagonally. And the initial question asks, what was this 0.8? So it just means in the 3-year-old or the 3-year-olds, the average birth rate is 0.8 of whatever the animal is per year. And that was the first question. And then we had this startup matrix. So there were 5 1-year-olds, 50 2-year-olds, 25 3-year-olds, and 20 4-year-olds. And the question was asking, what's the expected female population in the property at the start of the second year? So at the start of the second year, it just means at the end of the first year. So there's our Leslie matrix model. So I'll put this in. I haven't defined it yet, so if I just hit enter, it'll come up as this green colour. And then we can just do L times N. And that's the population of each age group. And if you wanted to add that up too, you could put in a row matrix. So because I used E before, I'll use Q, and I'll just define that. And this is going to be a row matrix. So it's going to be a 1, 5, 4. And it just has all ones in it. And so if I wanted to add all those numbers up there, I would just go Q times L times N. Oops. I'm not in a math box, so make sure you're in a math box. So Control M. So Q times L times N, and that will add all those numbers up for us. And wait a sec. Q, L, N. That's right, I didn't define it. Okay. Notice how I didn't have it defined over here on the right-hand side. So now it's right. So the last question, and this one was finding what the population was after 10 years or the beginning of the 11th year. So once again, it's just Q times L to the power of 10. So let's now just make sure you jump down. Times n, and it should add up all those for me. And the question was, if that's the female population, so there's 91 females and that represented 55%, what's the total population? And we have to divide by 0.55. So the total population was about 165. And finally, the last question, this cubic function passed through 3 points. So you could easily set this up as a system of simultaneous equations. And the command called the RREF command, so row reduced echelon format. So if you put in the A coefficients, 8, 27, 125, B coefficients, 4, 9, 25, C coefficients, 2, 3, 5, and then the digits that they equal, 2, 1, and 5, and then hit enter, there's our solution there. So A is a third, B is -793, and C is that. So yeah, using a math box, very handy tool, and I thoroughly recommend it. So thanks for listening. I'll hand over to Peter now.
Good afternoon all. I hope you can hear me and see my screen. So I'm going to spend a few minutes just talking about a couple of examples relating to vectors, in particular position vectors of a function of time. So the question here is a quite straightforward multiple choice question, and it says that the position vector of that projectile at time t seconds is given by that position vector. So what a position vector does as a function of time is it tells you where the particle it is at any time t. So the other thing to consider is we have what's called two parametric equations. The first one is x in terms of t. So the first parametric equation is x equals 10t, and the second parametric equation is y equals 19.6t minus 4.9t squared. So when you're considering projectile motion and you're considering an I component or a horizontal component and a j component or a vertical component, it's a good idea to consider the components separately. And the other point that I would like to make is that in the absence of air resistance, what we're going to see is that the path of the particle, the Cartesian equation that governs the path, is indeed a parabola. And you can see that because you have x equals 10t, you can therefore say that t equals x on 10, and then when you substitute that into the parametric equation for y in terms of t and solve, what ends up happening is that your first term is linear in x and your second term is quadratic in x. So therefore what you get y as a function of x being a quadratic, and so therefore we expect to see a parabola if we were indeed to plot the path of the projectile. So there are a few ways of solving this question, and I always like to sort of think about, well, can I solve it without technology first of all? And the answer to that is indeed yes, because it's quite a straightforward question. When you're looking for the maximum height reached by a projectile, what you're doing is you want to find the time, first of all, where the vertical component of velocity is equal to 0. So we have the y-coordinate, the y-coordinate in terms of t. So what we would simply do is find dy dt, so differentiate that component with respect to t, set it to 0 and solve. So if you did that, you'd get 19.6 minus 9.8 t, and then set that to 0 and solve, and you get t equals 2. And then the idea would be substitute t equals 2 back into that part of the position vector to work out what the maximum height is. You can also, if the question is a difficult equation to solve, you can also exploit the technology. So let's have a look at TI-Nspire, and hopefully you can see my screen there. So what we're going to do first of all is we're going to press menu. We're going to solve an equation, and we're going to solve a derivative set to 0. So in looking for the solve command, if we press menu and then number 3 for algebra, and then 1 or enter for numerical solve, then what we would like to do is we would like to press the catalog button, which is the open book icon, and we're going to select the derivative template. Our independent variable is t, and then in that box there, what we want to do is we want to type in 19.6 times t minus 4.9 times t squared. And what we want to do is we want to set that to 0, and we want to solve for t. And we could also, if we need to, we could specify a domain constraint. Now, because we've already thought about this, the maximum height occurs at t equals 2. It means that really we should be looking at the particle between t equals 0 and t equals 4. So we can add what's called a domain constraint to help us isolate where the solution is. That's actually a really good strategy if the equation you're solving has more than one solution. In this instance, the equation just has the one solution. So if we press, Stephen, do you press Control, then not that one, press Escape. What we press is Control equals, and then press the button to the left, and that brings up the with the given key, and that's how you specify a domain constraint. You press Enter, and then we merely say, okay, let's have 0, and we'll have that between, so less than or equal to p, and then less than or equal to, again, 4, and then press Enter, and our solution is t equals 2. So when t equals 2, we've got the maximum height, and so what we could therefore do is we could take the y coordinate, and we could substitute t equals 2 in there, t equals 2. And so the maximum height reached by the projectile is 19.6 meters. So what you're looking at, when you're looking at height, you're looking at the vertical part of the particle's motion. We can also look at this from a graphical viewpoint. So we go to a graphs page and we press menu, and then we, if I just press escape for a second, at the moment, if I pressed menu and graph entry edit, if we were to graph now, we would be graphing a function. We don't want to be graphing a function. We want to be graphing in a mode called parametric mode, because we want to be graphing what are called parametric equations. So if we press number 4, so what we get is our entry line that looks a little bit different. It doesn't look like f1 of x equals. You've got x1 of t and y1 of t. So for x1 of t, remember that the particle's position vector that we're dealing with is 10 times t, and then press the arrow down, and the corresponding parametric equation for y is 19.6 times t minus 4.9 times t squared. And the final thing now is to look at the allowed values for t and also the t-step. So by default, t lies between 0 and 2 pi, and the t-step, that 0.13, is actually pi on 24. Now, we're not dealing with trig functions here, so I think what we do is, and also knowing that the particle is moving over a period of 4 seconds, I think what we could do is we could delete the 6.28, change that to a 4, and for the t-step, because we've got a 19.6 and a 4.9, it might be a good idea to have a t-step of 0.1. Press enter, and we don't get a very good window whatsoever. Now, the key to this is when we go to menu, and if we choose window zoom and then window settings, here's the key to think about this. Remember that x equals 10t, and we know that t lies between 0 and 4. So therefore, if we think about that, an x max of 40 would be a really good move, right? So you take your t value and you multiply it by 10. So we could have an x in of, say, -5, an x max, say, of 45, an x scale, say, of 10. Now we've already worked out the maximum height is 19.6. So, you know, we've got good knowledge there. So our y max could be something like 25. And then we can tab all the way to OK and then press enter. And what we see there is that's our path of the particle. So it's a parabola, as we were discussing. And we can exploit the trace function here now. So we could press menu and then number 5 for trace, number 3 for trace step, just to see what it's like. Now it says automatic. We could make that 0.1 and then OK. And then menu and then 5 for trace and then 1 or enter for graph trace. And what you'll see is a tracer appears on the screen. And down the bottom right-hand corner, we have the starting coordinates, the initial coordinates, the initial position of the particle, and t equals 0. So now if you press your big button arrow to the right, what it'll do is it'll trace out the path of the particle every 0.1 of a second. So we're getting close to the apex of the particle motion. And we get there. So at t equals 2, the maximum height is 19.6. You can see the coordinates of the point there. The coordinates of the point are 19.6, and then continuing on, the particle's now heading down back towards the horizontal ground. So that's 3 ways of looking at that question. Once you've got x1 of t and y1 of t, you could go back to your calculator page. And you could press Control open bracket to get we can go Control close bracket there, the curly brackets, and we could type in x1 open bracket 2, comma y1 open bracket 2. Now notice that x1 and y1 have become bold and non-italicized. That means that the calculator recognises x1 and y1, and press enter, and that's another way of writing the coordinates. Remember, when writing coordinates on pen and paper, don't use the curly parentheses, just use normal rounded parentheses. Okay, so that's that question, and then the final question for today, if I can go back to the PowerPoint slide. This one has a couple of tricky parts to it. This is the position vector as a function of time. Now, in this instance, our parametric equations are x equals cos squared t and y equals 4 sine squared t. And so your mind might be thinking, well, what sort of Cartesian equation would I expect? Would I expect a circle? Would I expect an ellipse, for example? And that, that's reasonable to consider. However, if we look at thinking about what the Cartesian equation might be, we know that x is cos squared t, and we know that y is 4 sine squared t. So what we could do is we could multiply through by 4 for x equals cos squared t. So 4x equals 4 times cos squared t. And then exploiting the Pythagorean trig identity, 4 cos squared t plus 4 sine squared t actually equals 4. If we would add those two together, we therefore get 4x plus y equals 4. And if we rearrange that, we get y equals 4 minus 4x. So what we're expecting here is we're expecting a path which is a straight line rather than curvilinear motion. The other important thing to think about here is that cos t always lies between -1 and 1. Now we're dealing with cos squared t, so if we square through that inequality, cos squared t will lie between 0 and 1. You take anything and square it, and it's got to be positive. So if cos squared t lies between 0 and 1, then x must lie between 0 and 1 because x equals cos squared t. What I think is really important for you to realise is when finding a Cartesian equation, I think it's really, really important to also specify the accompanying domain, and that's what I've just described to you just there. So we'll finish up with a couple of minutes of looking at what the path looks like. We'll determine any intersection point with the coordinate axes, and we'll also see where the particle starts. Now, what's really important in these questions, a common question is to say, well, what's the initial position of the particle? And in particular, if we were dealing with a circle or an ellipse, is it travelling anti-clockwise or clockwise? Using the trace facility on Nspire, we should be able to determine that quite readily. So if we go back to Nspire and we go to a graphs page, now I've already taken the liberty to change it into parametric mode. So just as a reminder here, we're going to press trig and then cos and then t, come outside and it's squared, then down, and we'll press 4 times trig sine t, come outside there, squared there. And notice that our allowed t is between 0 and 2 pi, and that t step is pi on 24. It makes sense because we've got parametric equations in terms of cos and sine. So if we press enter, we get this result. And as promised, it is a straight line. Now, we could improve the window quite readily. This works quite a bit of the time. Sometimes it doesn't quite work as well as what I'd desire. You press menu and then window zoom, and then see down the bottom there next to A, zoom fit. So type in A, and what happens there is we get an automatic, well, pretty good fit there, and that's illustrating the Cartesian equation or the path of the particle. So this particle moves in a straight line. When we invoke the trace command, we need a bit of room down here because this is where the display always comes up. So I'm just going to make a minor adjustment to the window, and I'm just going to change y min to say -3, just so it gives it some room for the display there, that's all. Move that a little bit. And what we'll do now is we'll press menu and then 5 for trace. We'll have a look at our trace step. So I'm happy with automatic here. Press OK. Then what we'll do is we'll press menu again and trace. graph trace. And so, okay, that's lovely. What it does is it takes us to where the particle starts. So the answer to one of the question parts there was the particle, its initial position is 1, 0. And the other thing that was asked for was finding all intercepts with the coordinate axes. Well, the one up here, that's going to be 0, 4, isn't it? Because we've deduced that our Cartesian equation is y equals 4 minus 4x. When x is 0, y is 4. And so what we can do there is we can trace away. Final little thing is we can be a bit more exciting, and we'll press menu and then trace. And what we can do is we can go to number 4, which is path plot. We can choose parametric, and we can animate the we can animate the path of the particles. So we've got a button where we can press play, and that will trace out the path of the particle there. So it'll do that. It'll oscillate between 1, 0 and 0, 4 over a length of 2 pi seconds, because that's what our allowed t values are. So in summary, it's really important in these questions to first of all consider, do I need to use the technology? Can I work the question out without the technology? If not, then you've got many tools at your disposal. You've got numerical solve, you've got a numerical derivative command, you've got parametric graphing, you've got an animation feature, and you've got the trace feature. So once you work out how to answer these questions, I find them quite enjoyable and easy to solve, and hopefully you do as well. So all best on behalf of Stephen and I and Emily, best wishes for your exam. Thank you.